Now, stock price prediction is a very, very popular thing that a lot of people have looked at. Very, very popular. But like I said, before we look at a stock price prediction, you need to understand the machine learning model, the several machine learning models, over 15 models that are needed before you can undertake stock price prediction. It is what is regulating the entire stock market. It is money. People are making a lot of money in the stock market because of the capacity and the skill in predicting the rise and fall of asset prices. But before we can do that, you need to understand specific machine learning models. So when I mention the machine learning model, you tell me whether you have learned it. Linear regression. Have you learned it? And when I say learned it, I mean you can practically use it. Either using a software like Python or R, or basic Excel. Linear regression. Have you done it?
Yes, sir.
So when you're given a data set of target variable and several features, you can construct a linear regression model, right?
Yes, sir.
Ridge regression.
For me, no.
Okay. Ridge regression will need linear regression and something else added to it. Lasso regression.
No, please. I have not.
Elastic net regression.
The same. That's for me. I don't know for others.
Tell your colleagues to bring their video back. Logistic regression.
No, please.
Support vector regression.
No, I've heard of it, but then I've not gone into details.
Yeah. All that I'm asking is about going into the details. The support vector machines, we have the classifier and then we have the regression. The classifier is used in classification, then the regression is used in regression. They are all support vectors. K nearest neighbor.
No, please.
The same thing with the K nearest neighbor, you need to know the classification part, especially because you are dealing with classifiers. And then you need to know the regression, okay, where you are dealing with, actual numeric variables. Now, the support vector machine, after that, we have the decision trees. There are several of the decision trees and ensembles. So you have the decision tree for the classifier, and then you have the decision tree for the regression as well. One uses the classification, the other uses the regression. Have we done decision trees?
No, please.
Random forest, the same thing for the regressor and the classifier. Gradient boosting, the same thing for the classifier and then the regressor. Extra trees for the classifier and the regressor. SG boost, okay, that is an addendum to the gradient boost. The light GBM, which is gradient boosting, approach. It is also an addendum to the SG boost. The CAT boost. All of these are decision trees and ensembles. You have to know naive Bayes models. All of these are supervised machine learning models. Gaussian, naive, multinomial, Bernoulli, the neural networks family. Okay, Either it is multi-layer perception or perceptron for classification or for regression. You got to know that as well. And there are more. So these methods, you got to know them, before you apply. Otherwise, when you're applying them, you get stuck. But you got to know them. Discriminant analysis is used a lot. In fact, I'm supervising some students who are using 7 of these models. Discriminant, you have the LDA, the linear and the quadratic. And then you have other ones, which are, specialized. So you're supposed to know these things actually before we actually started this topic. And from the little I know, it appears that you have not known. So what I'm going to do is, I'm going to take some time. It's supposed to be brief, but it can't be brief. It has to be a lecture. To walk you through the linear regression, then you can understand. So what is a linear regression? A linear regression builds a relationship between 2 variables, 2 major variables. The target variable, which is a dependent, which is a y, and then the predictors or the regressors, which are the independent variables. So here you have the y, which is a target variable, is numeric or metric. And it is dependent on several independent variables, which are explanatory variables, sometimes also called features. These variables are many, but you don't normally want them to be many. I'll give you a couple of examples. For example, the quantity demanded of any commodity is affected by the price. The quantity demanded is a dependent variable, the price is the independent variable. But there are other factors that can affect the quantity demanded in addition to the price, like income, like complement price or substitute, like population, okay, like price expectation. Some people talk about taste and preferences, but it's very difficult to measure unless you have the principle of ordinary utility and other factors. Of course, in fact, even advertisement can affect it. But there are more factors that we cannot capture. And all of those factors are said to be the error term. These error terms are disturbances. They disturb the relationship between the dependent variable and that of the independent variable. Another example you can think about is the blood pressure of a person. The blood pressure of a person is affected by the weight of the person. It's affected by the age of the person. It's affected by the, if I ask you, normally I ask you, okay, the stress level of the person. What do you think can affect the blood pressure of a person? Weight, age, stress. I'm not talking about affected positive or negative. Any one of them is fine. Okay. Which factors can positively or negatively affect the blood pressure of a person? Give me one factor apart from what I've listed. Exercise. Diet. Other diseases. Other diseases can also affect the blood pressure of a person. And of course, there are so many others. So these factors you are seeing here are the features or the explanatory variables. You want to know the contribution of each one towards this dependent variable. To what extent does weight affect blood pressure? To what extent does age affect blood pressure? To what extent does stress affect blood pressure? And then on and on. These factors are in this arrow, and they are the ones. So you will get data on blood pressure That data is the YI. That's the YI. That is the actual value. And then the errors will make the YI different. If the YI is the same as YI here, then the error is going to be 0. So for each observation, we will be able to find the gap between the actual and the predicted. This is the actual, this is the predicted. The gap between them is the error. This error is what we normally call the cost function or the loss function in machine learning model. Why is it a cost? It's a cost because it's an error that you want to reduce. Why is it a loss? It's a loss because it's negative, it's bad, that you want to reduce. So the essence of a machine learning linear regression model is to minimize the error, ideally. But in principle, you are not minimizing the error. Why? And this is why. You see, this is a general model of what we've just explained above here. So I've put all the Xij, because there were a number of them at the top. I've put all of them together. So you have the target variable on the left, and then you have the independent variables, some of them, and then the error. The beta naught is just a constant or intercept, which is when there is no independent variable. When there is no independent variable, sorry, when there is no regressor, then Y will be dependent on the beta naught. This beta naught is usually for cosmetic purposes. It's for beautification. Okay. Now listen. We can estimate this model and find the relationship between this target variable yi, which in our case is a what do you call it? Is a blood pressure. In fact, we can specify the model. So you can say that blood pressure, okay, for a particular individual, I, is equal to the beta naught plus the sum of all the independent variables. Let's just pick one. Let's say beta 1 weight. So I just focus on weight. And then I add my error. So this is a specified model. Now, I need to find something we call the residual. The residual is the same as this error. The residual. What is the residual? The residual is defined as the actual quantity you have gotten minus a predicted. This actual minus a predicted. Remember, this is what you have actually estimated. That's what you've estimated. Okay. And then what you have here is what is actually there. And you want to check whether what is there deviates from what is estimated. The gap, the deviation is a residual, the epsilon. This residual, actually, it is given by what is on top here. But the point is that there can be negatives here. For example, in case this yi is 2 and this yi cap is 4, the value can be what? Negative. And you don't want negative value. So in order to remove the negativity, you square this one. So that whatever the difference this one is, it will be positive no matter what. Squaring this is what we call the residual sum of squares. So the square there is squaring this. Okay, so now I decide to square this. And now I can sum the errors. Remember, I've taken the square. The square is just to eliminate, or get an absolute value. Then what you do now is to sum all the squares. There is an assumption here that the expected value of the error should be 0, which means the mean of all the errors. Some of the errors are positive, some of the errors are negative. The mean should be 0. In other words, by the time I get my relationship between blood pressure and weight, every other thing, which is error, that can disturb the disturbance thing, that can disturb the relationship. Every other thing has to be what? 0. Which means there must be nothing else infiltrating in the relationship. The relationship must be clear. Take, for example, a marriage relationship or a romantic relationship. That relationship is affected by several things: love, money, in-laws, sex, and so many other factors. Each one plays a role in affecting the relationship, but there are other factors that can affect the relationship. You want to minimize those other factors that would disturb your relationship so that your relationship will be strong. So you want to minimize the errors. You want to minimize those external factors that can affect, and that is the residual sum of squares. So now I add a sum to the errors, which is a residual, after I have squared it. The residual sum of squares is what we call the cost function, the loss function. And the goal of the regression is to minimize it. Minimize it to the barest minimum. The minimum you can ever go for is 0. The residual sum of squares is this. So when you look at this, what I wrote above, that is what you have here. When people see this, they start thinking it's Hebrew. This is a RSS. The goal is to minimize the RSS, the residual sum of squares, with the intention of coming out with the beta, which is the extent to which an independent variable affects the dependent variable. The extent to which each feature affects the target. That extent to which you affect the target is the beta parameter. And then the equation we had, in a simple equation, this is what we wrote before: square it, then come and drop this one. This one is the original equation. Drop it here. And at this stage, you can use a principle of minimization to come out with the betas. Remember, you have the beta naught here, and then you have the beta j here. How do you find it? You can take the derivative of the whole thing with respect to beta naught. And then you can take the derivative of the whole thing with respect to beta j. The most important one is the beta j, or the beta, the one that is attached to the dependent variable, the independent variable, which is the x. How do we find the beta? Well, we minimize the error sum of squares. Set it to 0. You remember the principle of minimization. You minimize something, set it to 0, then use simplification to come out of it. That is what you can do here for that. It's very easy. And we use that to be able to come out with the error. I can go through that, but we don't have time. This is what is known as OLS, ordinary least square. It's the easiest of the regression one can do. It has an easy advantage that you can interpret the whole thing easily. It is what is called a foundation. It is a one that you can train. And when you are training this model, it's cheap, computationally, very cheap. No waste of time on anything. Training the model is called fitting the model. Fitting the model is throwing a line, the line of best fit, into the data point to see the relationship. We'll do that practically. And it is a foundation for all the other regularized regressions we shall do: the Lasso, the Ridge, the elastic net. So you cannot know the rest unless you know this, because this one must be known. It is an RSS that you are minimizing. It's a loss function. Once you get that loss function, you add some things to it, which now takes us to the Lasso, the Ridge, and the elastic net. So it's a foundation. And once you get a coefficient of the OLS regression, they will directly tell you the marginal effect of each feature on the target. I've said it. What is the effect of weight on blood pressure? What is the effect of diet on your blood pressure? What is the effect of this on the dependent variable? The coefficients will tell you. If it is negative, the effect is negative. If it's positive, the effect is positive. Now, along the line, you'll be doing hyperparameter tuning. And that is a very simple grid search that you can use to find good settings, okay, very, very quickly in the model. We can look at that. The problem with the regression is that the hyperparameter tuning is not good enough. There are few hyperparameters that you can tune. You will understand this practically. The other problem with that, it assumes linear link. You see, it assumes that the relationship between the dependent variable and the independent variable is linear. It's a straight line. What is this? This is a negative relationship, but it's linear. When one goes up, one comes down. When one goes up, one comes down. What about this? It is also a positive relationship, but it's still linear. They're all going up, they're all coming down. They're all going up, they're all coming down. But what is this? It's not linear. It can be linear, a quadratic. A relationship can be non-linear. For example, something can rise, get to a point and fall. Such a thing is not linear. Linear is when it is rising, 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 like that. Linear is when it is falling, 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 like that. But non-linear, it can rise and fall and rise and fall. That is sort of quadratic, parabolic, and so many things. Regression assumes linearity. But what if the data is not linear? That is where regression becomes an issue. So that is one downside. So we've indicated that it may not work under a situation of non-linearity. Also, there could be other issues like multicollinearity. What is multicollinearity? You do all of these things in your thesis. And I'm giving you, you would answer some of them as well. What is multicollinearity? Multicollinearity exists when two independent variables are so highly correlated. Two explanatory variables are so highly correlated that it becomes difficult to disentangle or separate the partial effect of one from the other on the dependent variable. Let me give you an example. Salary and wage. Which one do you think is the explanatory variable or independent variable? Salary and wage. Which one is the independent? Salary and wage. Which one is independent? Nobody. Which one affects the other? Which one?
I think wage affects salary.
Oh, sorry, I think I made a mistake. I'm talking about salary and experience. Sorry, it's my fault. Salary and experience.
Okay, then experience affects salary.
Okay, what about salary and education?
Education, it depends on the context in which we are considering the variables. So if we are relating
your wages you get, your monthly wages you get on the job, okay, and your level of education, which one affects the other?
So the education affects the salary.
Good. So here's the thing. Your salary is a function of your education and your experience. However, suppose you are in a company, the company tells you that, okay, you are in a company and you realize in the company that every time somebody goes to do his MBA or PL or MBA or MSc or MPhil, anything, somebody goes to do the masters and the person comes back to the company, the person's salary is doubled. You have witnessed this for 2 years in the company. You don't understand why. So you were angry and asked your boss. Your boss tells you that, what is your problem? You said that my problem is that I've been here for 2 years and people are just going to do masters. When they come back, their salaries are doubled. Why? The boss said, oh, sorry. In this company, after you work with us for 5 years, you will be given a full payment to go and do your masters. And when you return, your salary is doubled. So now, you know it's not time yet for you. How many more years do you have? Hey, Rabina, how many more years do you have?
3 years.
Now, because you know you have 3 years, your 3 years came, you were actually given all the money you need to do your master's. You did your master's, you came back to the company, they doubled your salary. Question is, what led to the increase in your salary? Was it the experience you had or the education you had? Was it experience or the education set?
The education.
Okay, Richmond. Which one?
Education.
The Rabina, which one?
The education.
None of you is correct. In fact, it tells me clearly that
But
most
I
of you
think
are
both.
guessing. Most of you were
Both
just guessing
education and experience.
and you were guessing and then doing everything that you can. If you had not had that 5 years education, there was no way you would have actually had your schooling. And if you had not had your schooling, there's no way your salary would have been doubled. The two of them are interacting with each other to affect your salary. Now, the reason why you are even confused in the first place is because the two variables are multicollinear. That's what we mean by multicollinearity. Multicollinearity exists when two independent variables are so highly correlated that it becomes difficult to separate the partial effect of one from the other on the dependent variable. It becomes difficult to separate, disentangle the individual effect of each one on the dependent. So in this case, one of these variables is redundant and it may have to be removed from the model before the other can, because other than that, the two are them. For example, let's say that your husband steals money from the workplace on 24th of December. Then he was caught, arraigned before the court, and then you were told to come and defend the issue. Then you were asked that, was your husband with you on the 24th day of December at 6 p.m.? If you're a bad woman to your husband, you say no. And that will finish your husband. Okay. If you're a good woman to your husband, you say yes. But the court knows that the two of you are too close. So the tendency for you to support your husband is high. The jury will know that. And so we do not normally allow people to defend their spouses on matters like that because of the closeness. That is called multicollinearity. Multicollinearity happens when two factors are so close that you cannot even tell which one is leading to the actual cause. This problem is a huge problem in a regression because when it is there, the coefficients can be affected, the t-stars can be affected, the p-values can be affected, the interpretation can be affected. This problem can be handled. And you will see that it can be handled when we go to other models. But in the OLS regression, it's a problem. Regression is also sensitive to outliers, extreme values. Okay? It has an issue of overfitting and underfitting. You will see that. You got to read about all of these. Okay, there is no feature selection. Okay, it can bring about hope. It assumes homoscedasticity. When in reality there can be heteroscedasticity. It assumes that the variances are constant over time when it's not really constant. It assumes that the individuals are the same. When individuals are not the same, you are different from me. There is something that makes you unique, differently from me. Regression says that there's nothing that makes you unique, differently from me. And then it also assumes that there is no autocorrelation of errors. Remember the errors. The errors are the deviation from between the actual and the predicted. But regression says there is no autocorrelation of the errors. sorry, let's say regression requires that there is no autocorrelation of the errors. Okay, but there could be autocorrelation of the errors. The errors could be autocorrelated. Autocorrelation is when two errors are related to each other. The key point is that when things are related to themselves, it's very difficult to put them both in a model. In short, regression has issues. So we need to find a way to address those issues. How do you handle the issues of the regression? And whenever you are doing regression, you got to tell the reader that you've handled all of these issues. So one way to handle the issues is use regularized regression. Regularized regression is when you have your regression and you add a penalty. You add a penalty function. That penalty function is called regularization. It will help you to handle overfitting and multicollinearity. So the OLS is minimized. We know this. This is the OLS when it is minimized. This is a residual sum of squares. You know this from the previous one. Now, if the data has too many features, like the x's are many, independent variables are many. If the features are highly correlated, like what we just said, if they are highly correlated, it means that they are multicollinear. There's a lot of multicollinearity. Or if you have a problem of overfitting, okay, if you have overfitted training data, not the test data, the training data, the OLS will not work. It will not be reliable. Why? Why? And this is why. Because the OLS will do proper fitting of the model. And when I say fitting of the model, I'm talking about the training data. The training data is basically the data you use to build a model. That data, we normally have 80% of the data, which you use to build a model. Okay. But even if the data is fit well on the training data, I mean, the model fits well on the training data, it will surely fit poorly on the testing data if those problems I've said exist. If those problems are there, if there are too many features, too many independent variables, highly correlated independent variables, overfitting of the training model, if these things are there, the OLS will do well on the training data, but will do poorly on the testing data. And note that the testing data is different from the training data. The testing data, which is usually about 20% of the data, is that part of the data which is used to test how good the model is. The training data is used to build it, but the testing data is used to test how the built one is good. And so if you have a training data that is doing well, but then the testing data is doing poorly, okay, then we have an issue of overfitting or high variance. So what the regularized regression will do is this. It will add a penalty. It will add a penalty to solve the problem. What is that? This is it. So you have the usual residual sum of squares, which is the RSS. Take note of this. Remember, this is the one up here. That is the one up here. Okay, the whole of this one up here, that is this. And then you add a penalty on the coefficients. So the coefficients are the betas. That's the one you're looking for. You add something small to that, not on anything, on the coefficient. So now you have the residual sum of squares plus the penalty on the coefficient. And then you have a new loss function or cost function. Then you can come and minimize this new loss function or cost function. Now, there are three major regularized regressions around. Here's the first one. Lasso. Do you have that one here? Okay, we'll talk about the Lasso very soon. But let's look at the advantages of the regularized regression. One of the main advantages is that it shrinks some of the coefficients. It shrinks them. Shrinking is something becoming small instead of it becoming big. It also shrinks some of the irrelevant features. What do I mean? Let's say that we are looking at the factors that affect blood pressure, okay? And then you go and talk about, okay, let's look at factors that that affect, let's talk about blood pressure. And everybody is talking about weight, exercise, and then you decided to talk about broken heart. Broken heart does not lead to high blood pressure. So many people have had broken heart, they're not having high blood pressure. So, but if you force to include broken heart, because you believe that broken heart, because it's on specific cases, it's not general, so you can't include it. But if you decide I'm going to still include broken heart is an irrelevant feature. It's not relevant. It's not a relevant independent variable. And if you include that, you are punishing the model. The R square we have to reduce. It doesn't reduce. That's why you have an adjusted R square that punishes you for that. What the regularized regression would do is that it will shrink those irrelevant features so that they don't even come into the picture at all. It's a very good thing. Again, the regularized regression, because it is introducing a penalty on the coefficient, it will improve the generalization of the model. It will prevent overfitting. It will handle multicollinearity. And then it can even improve the test performance of the model. In terms of prediction accuracy, because it's already shrinking, the coefficient or setting some coefficients to 0. Because remember, when I say coefficient, suppose you have coefficient, one of them is beta 1, you have beta 2, you have beta 3. For every independent variable, you have beta 4. And now it's set beta 2 to 0. It means beta 2, that independent variable is gone. Because when you multiply beta 2 by x2, the x2 is gone. It's finished. So by doing that, by setting some of the coefficients to 0, we are trading off the capacity to fix complex models. Because if the thing is plenty like that, it's complex. But when you set betas to 0, the independent variables are no longer there. So that the models breaks down, then we have a very simple model. And complex models brings about higher bias. When the model is complex, there's a lot of the potential to making errors. So what it does is that it is able to shrink the model to fit the complex model for a more generalizable model. So once we now have a simple model, we can now have a low variance. And now we can generalize the result. So regularized regressions are quite good. Now, but one slight problem is that it can underfit. Suppose you put a penalty. We said that you have the residual plus the penalty. Okay. Suppose the penalty is too strong. Okay. You can underfit the model. It's trying to do overfitting, stop overfitting. It's trying to stop overfitting, but it will rather can cause underfitting. So suppose that they say you should run. Running is good. You are running. So because they say you should run, you are running. Then you see people have cardiomyopathy on the pitch. You see some footballer, he's playing football so well, then boom, he falls down, he dies. Mark Vivian Foy. The person died because he may have taken things to the extreme. Regularized regression can do that. So you solve the overfitting problem, but now you bring a problem to what? Underfitting. Let's take the first one, Lasso. I told you that it is just the normal regression you have, but this time you are adding what? You are adding a penalty. Okay. So you have the error. So we are going to have a new cost function, but that cost function is the RSS. Okay. So there's a typo. The RSS should be, let me show you. So it should be RSS plus this. Okay. The RSS is the same as this one. Okay. So it's the RSS. Actually, it's supposed to be the RSS plus the L1. Okay. The L1 is this one here, the penalty. So it is this RSS plus that, or the whole of what I've circled here plus this thing. Now watch this term. This term is the penalty. Penalty that is added to the residual. What is that? Look at it carefully. It is the lambda that you are multiplying it by the absolute value of the beta. No. So this lambda, this beta is the beta for every independent variable. So each one of them is multiplying some lambda. And the lambda, the value of the lambda will determine whether that coefficient is going to go down or go up. Of course, if the lambda is 1, then this thing, when you multiply 1 by whatever is here, you get the same thing back. So if the lambda is 1, we are back to the OLS regression. That's all. If this lambda is 1, we are back to the OLS regression. That's the idea. If there's anything else there, then we have a penalty. If lambda is 0, we are in a different section. So the goal is to regulate that lambda. It's like fine-tuning the lambda.
Okay. Okay.
Yeah, normally it happens when people are not paying attention. That is when I know that they don't even know that their talks are coming around. All right, let's see how to address this. So you have lambda here multiplying the beta parameter, the absolute value of a beta parameter. That is a penalty. That is what is going to shrink the coefficients towards 0. Okay. Now in the OLS, we minimize the error sum of squares or the residual sum of squares. Only the RSS, which is what I told you. But in Lasso, we punish the large beta parameters heavily. We set the lambda to 0. If you happen to set the lambda to 0, we are, oh, I said we set it to 1, but it's supposed to be 0. I think I made an error. I made a huge error. Look at it. If this one is 0, then the whole of this is gone. Okay. If this lambda here is 0, 0 multiplying the whole of this is 0. So the whole of this is gone. So we are back to this one. So we are in the OLS regression, the pure linear regression. But if lambda is 1, okay, that's the highest value that this one can take. So lambda is circling between 0 and 1. Now, so lambda must be increased or decreased. Okay, lambda must be increased. Remember, it's a ratio, so it's 100%. Now, if lambda is large, I've not said it's 1 yet, but let's assume it's very large, then almost all the features set to 0, okay, that might lead to underfitting. Now, if lambda is moderately high, okay, so large means that you set it to say perfect of 1. So it means that you've underfitted the model. But if you set it moderately, then some of the features will be zeroed out. Okay, not exactly all of them, because you can have 0.00 something. Some of them will be zeroed out. So the essence of it is to choose the right lambda. And choosing the right lambda is called hyperparameter tuning. So you do that using a grid search in R. And you can see that when we get to the practicalities to that. But the key point I want you to understand of Lasso regression is that there is a lambda multiplying the absolute value of the beta, which is added to the residual sum of squares. That is what we mean by Lasso. Finish. So in case you've heard about Lasso regression, that's it. And the essence is for it to control the beta parameter, the coefficient, so that they are able to do proper estimation and proper prediction. Now, by the way, Lasso regression is also called L1 regularization, just so you know. It solves the issue about the underfitting of the model. Okay, and it helps in feature selection. Sometimes it's called sparse selection of the. In other words, it helps you to identify which independent variable is good, which one is bad, which feature is useful, which feature is not useful. The next one is L2 regularization. It's not Lasso, but it is range. Again, look at it. It is the same as the Lasso, but But this time, look at it. The lasso two, we had the lambda here. And then this one too, you have this here. What do you think is the difference between the lasso and that of the range here? Remember, they are all having this. Okay. They are all, I mean, if you look at it here, you see. They are all having the RSS plus something. What do you think is the difference between the lasso? Mathematically. Yes. Who was talking?
Yes, Doc.
Go ahead.
The betas are squared before multiplied by lambda.
Mm-hmm. And then?
Okay, that's all I see.
And then what about the other one? You're comparing it with the lasso. What about the lasso?
Okay, in L1, the betas are not squared before summed.
Now what are they?
They are summed up and then multiplied by lambda, then added to the RSS.
I know. You let's forget that all of them are added to the RSS. But what is in the lasso? That is not here. That is, if you were paying attention, you would have seen. You said that here the betas are squared.
Yes.
Forget about the summing part. Forget about being multiplied by lambda.
Okay,
fine.
and yes, so in the lasso, we took the absolute values of the betas.
That is the most important thing we need here. That is the important thing here. Okay, you see, so that one, you don't square it, you take the absolute value. So the whole idea is that you are making it positive, both of them. When something is negative and you square it, you're going to get negative. You're going to get positive. When something is also positive and you square it, it's still going to be positive. When it is whatever number and you take the absolute value, it's also going to be what? Positive. So you can see that both lasso and rage are trying to positivize the beta in different ways, in two easy ways. One is squaring it, the other is taking the absolute value. Whichever way it is, as many of them as they are, they'll become positive before they are added to the residual sum of squares. Okay, so now that's what you're going to minimize. Okay,
Sorry, I had a little question just before you. I wanted to find out if the lambda here has a range of values.
Yes, it does. It's between 0 and 1.
Okay, thank you.
All right. So now let's go to how it does a minimization. I'm not going to show you. I will show you a simple example rather. Okay. So this model, oh, by the way, when you look at this model, you will notice that you can minimize this whole function. Okay. Minimization, optimize it, means that you differentiate the left-hand side with respect to beta naught. Then you differentiate the the left-hand side with respect to beta j. Okay. Now you get an answer. Of course, this is a multiple regression. As you can see, there have been some here, so we can't do that. I'll take a simple example and show you. So P is a number of features, as you can see. Look at the top there. Okay. Unlike this one, it is the number of observations when you look at the left-hand side, but with the penalty function, the penalty on the coefficient, it is up to the number of. So you do this for every feature, every independent variable. So if the independent variables are 5, there are going to be 5 other betas that are going to be multiplied by lambdas. That's the whole point. Okay. So the penalty, which is the lambda, it regularizes the betas. That's why it is called regularization. Now, in range regression, the model prefers smaller coefficients. Smaller is better. So shrinking them, but never making them 0. That is a whole idea. Okay. Now, if you shrink them to 0, we are back to the OLS regression. We said that. That means that you are going to have a lower variance and an error. If it is large, you're going to have a very strong shrinkage. So the shrinking is going to be very, very strong. The coefficients become very tiny, and the fitting may occur. And you can use this command in Python to be able to do this. Okay, let's go to the last one. The last one is very easy, even though it looks complex, but it's the easiest. The last one is elastic net. You see, you can set the lambda between 0 and 1. Elastic net, what it does is that because of the possibility of underfitting by range and overfitting of Lasso, what the elastic net does is that it combines all of them. So you have the OLS RSS, which is a residual sum of squares. Then you add the penalty on the Lasso, which is a L1, penalty on the range, which is a L2. So you add those two penalties and then you combine them. That becomes elastic net. So it's like you are using all of them together. That is elastic net. So it's like a net that is so elastic that it can hold all of them. Now, look at it. Oh, by the way, look at it. If you look at it here, you see that this is the OLS residual. Okay. There's the OLS. Then this second one here, which is now lambda 1, that is the Lasso. And then the lambda 2 multiplied by the whatever is the range. So you can see that the range is having the beta 2, the Lasso is having the absolute value. Each of them have got their respective lambdas. And that is then added to this. And then you minimize this whole function, which becomes elastic net. So look at it. That is an elastic net. The same thing, different way of writing it. Okay. You put them together, and then you set this one equal to that. Now there's a typo I've made here. Who can see it in this equation? Who can really open his eyes and spot it? In the bracket, in the one in the big bracket, there's a typo. Forget about the alpha. After the alpha is just the same thing. You see, I still use lambda here. So I bring lambda out. Lambda multiplying by this alpha will give us lambda 1. Lambda multiplied by 1 minus alpha will give us lambda 2. That's not a problem. The problem is the n here at the top of the summation sign should be what? The n
it should be a p.
Excellent. Very good. You're controlling. You're controlling. Let's move on. So the lambda will control the overall strength of the regularization and then the error. Lambda, the alpha is between 0 and 1. It controls the mix between. So if you want more of Lasso, then you will now move the alpha. So if you want more of the Lasso, you give this one, say 0.8. And then you give this one automatically become 0.2 because you want to put more emphasis on the Lasso. If you want to put more emphasis on the range, then you make the alpha so tiny so that the 1 minus alpha attached to the range will become bigger. So alpha controls. Which one is your? If alpha is 1, what do you think will happen here? If alpha here is 1, then 1 minus 1 is what? 0. 0 multiplying this is that. So we now get pure Lasso. Do you realize that? It means our range is not there. So 1, let me write it here. I just hope you are following. It is your question that will make me stop. So you now have 1 minus 1, that is 0. 0 multiplying this whole thing, the range is gone. Range is gone. We are now left with pure Lasso. But if lambda is 0, you can see that we have pure range. Because if lambda here is 0, then Lasso is gone, then we are left with pure range. So lambda is between 0 and 1, a blend of both. It's cool, man. It's cool. It's cool. This is a penalty. Now we are done. How do we solve that in a practical data set? Now let me put a clause here that for all regressions, a lambda is the key parameter to tune. We are not interested in tuning alpha per se, but in the great search in Python, we will tune the lambda. In the elastic net and quan, that is the one you tune the alpha, because in the others, in the range and in the Lasso, there's no alpha. So it is in the elastic net alone that you have to tune in both alpha as well as lambda. Other than that, hyperparameter is on. And that is a slight problem. The reason why many people don't like using the elastic net, even though it can help. Let's take a practical example. Are you ready? I'm giving you, this is how when you are presenting and when you want to understand a model, this is how you do it. Learn practical. Let's take a data set. I don't know, this data set is is something. I don't know what it is. Let's say that this one is a quantity demanded of something, and this is a price. Now, this cannot be quantity demanded, because you can see that as the price is increasing, the quantity is increasing. So this means that it's quantity supplied. Okay. So you sell goods. You sell goods. And this Y here is your supply. Okay. So you will supply more. You move the supply from 2. Let me circle this so you can see. You will understand this with this example. If you don't understand this, I don't know what kind of witches and wizards are in your family. Okay. Now, this is supply that you supply goods. You supply 2 when the price is 1. You don't want to supply more, except if the price goes up. So if the price goes up from 1 to 2, you decide to supply more. Now, if the price even goes up, you supply more because you know they are going to get more money. Okay? So this is a typical example of a situation that is showing a positive relationship between the price of a commodity and then the supply or the quantity supplied of that. I'm just hypothetically giving you something. All right, let's move on. So we've learned about 3 models here. Okay, there are 4 models actually. You're going to put all of them together. So let's try to first of all look at the regression, because the independent variable is only 1. The feature is only 1. We have only x. This is a specified model. The error term is there, or the residual is there. Now this is a summation. Okay, we have the y minus the beta. We are minimizing this. Remember, the only x is xi. So xi is like x1. You're going to minimize this. Now, if you want to minimize this, I'm telling you, if you work it, you're going to find the beta value to be this. If you minimize this thing, if you minimize this subject to beta, okay, when I say minimize subject to beta, I'm sure you understand. If you minimize the subject to beta, you will differentiate this one. There's 2 here. The 2 will come and multiply this and set it to 0. So you will differentiate this, okay, set it to 0 and find the value of beta. You're going to find this answer. Once you find this answer, it's very easy to find this other one. Let me tell you why. How do you find the beta naught? Imagine this thing is 0. Given the assumption of regression, imagine this one is 0. How do you find beta naught? Beta naught will be equal to, you move this one to this side. So you're going to have y minus beta 1x, isn't it? At the moment you do that, y becomes a mean. Y becomes the mean. X becomes the mean. So beta naught is actually given by, once you've estimated the beta 1 here, then this one here becomes the mean of y minus the one you found times the mean of x. Okay, so let's find this. How do you find this? Substitute them. XIY is this. How do you find that? It's very simple. Take 1 here, multiply it by that. That is xy. So take this x, multiply by that. That gives you what? 2. Take this x, multiply by that. That gives you what? 8. Take this 3, multiply by 6. That gives you what? 18. Okay? So that's what you are seeing here. 2, 8, 18. Add them all together because it says sum. We are trying to find this. Oh, we are trying to find this beta. Add them all together. What do you get? 22. No, sorry, 28. Okay. Now it says that we should divide it by x squared. So let's go to the x. Let's square 1. That will give you 1. Let's square 2. That will give you 4. Let's square 3. That will give you 9. That's what is here. So 1, 4, 9. That gives you what? 14. So now it says that you should take the numerator by the denominator. The numerator is what? 28.
8.
The denominator is what?
14.
So you now have 28 divided by 14. The beta is 2. Now let's find this one now, the beta naught. I have found the beta 1, okay, according to this formula. So the estimated value is beta naught cap, okay, plus beta 1 and then x. I've estimated it. I just found this one to be what? To be 2. Now, how do I get this? All I need to do is to find the mean of this. And find the mean of it. Let's go to the x and find the mean. The mean of x is 1 plus 2 plus 3 divided by 3. What is that? 2. Okay. The mean of y is 2 plus 4 plus 6 divided by 3. What is that? 4. I hope you guys follow me. So now, how do you get the value of this? We know this is 2 already. We just found this one, the mean of x to be what? To be 2. So you now have 2 times 2. And then you find the mean of the y to be 4. Okay. So if you want to get this value, it's 4 minus 4. Because when you multiply this, you get 4. So it becomes 4 minus 4. So beta naught is what? 0. This is what we call perfect fit. So beta naught is not needed. So we've been able to get this value. So if I want to write the equation becomes y cap is equal to 2x. There's no need for beta naught. Beta naught is 0. This is OLS. This is OLS regression. No noise. You can solve it in Python. Let's go to Lasso. The same thing. Now, this is the Lasso equation. Okay. Now, Lasso is doing something that is very funny. Okay. Now, Lasso will minimize this one and add this thing to it. Now, because there are not many betas, okay. Where is this thing? 1 second. Because there are not many betas, you don't need to bring that summation symbol. You don't need that. The beta is only 1, which is beta 1. So we just have this. So it becomes a lambda multiplying the beta. So we don't even need to have beta 1, beta 2. We just have beta. Okay. So we have the original residual. Let's add the beta to it. That's what it does. Now watch something. There is no closed form solution like Rage when it comes to Lasso. But with a small data set and assuming no intercept, we can use what is called soft thresholding rule. Now, what it does here is that it uses a certain principle. Okay. The principle is where you maximize this, of course. You minimize, you normally would minimize this, okay, but you would have maximized the softness of this because we've assumed that beta naught is 0. Okay, because beta naught is 0. Your focus will be on getting a threshold that will minimize the rest of the things related to only this one here, without even considering the beta naught. When you also use Python, please note that Python will normally do what we call scaling and normalization. Okay, scaling and normalization. And because of that scaling and normalization, okay, you got to incorporate that into the picture. So when you do this scaling and normalization by maximizing the 2 binary sections of 0, because we've assumed that beta naught is 0, you're going to get the z, which is a sigma xy. You're going to have that to be the same 28 as you had before. And then you had the bottom one to be this. Now, in the beta naught of the previous one, we saw that that was equal to 1. But now, let's assume that lambda is 1, because remember that we don't know lambda, so we got to assume that lambda is 1. Of course, we know that when we assume that lambda is 0, we know what's going to happen. So let's assume lambda is 1. If lambda is 1 and you substitute that into this function, then we are going to have sine of the z, and the z, it is 28 here because it's the summation of xi, yi. And then you take the maximized value, you have this function, which is a lambda, which is 1 divided by the 2, making you have 0.5, because that's half. 25 minus half is 27.5, divided by the 14. once you have this divided by 14, what are you going to get? You're going to get, because the maximum value of this is 1, so you're going to get 20 points. So that's going to give you 1.964. So under the lasso regression, you're going to have 1.964. Now, don't worry. If you use software is going to give you this value anyway. Okay? But watch the difference. You can remember that under the normal regression, it was 2 for the OLS. Under this lasso, we are getting 1.96. So lasso has brought what? The coefficient slightly down. Let's go to the last one. The last one is the range regression. Now, the range regression will also minimize this function. Remember, nothing changes here. The slope formula is this. It's very simple because we know this value to be 28. We know this one to be 14. All we are going to do is to divide. When you do the minimization, you're going to get this. You divide this, add the lambda to it. We've already assumed that lambda is 1. Guys, this assumption of lambda is 1, it is a very common assumption that the software even uses. So once you assume that lambda is 1, you substitute that 1 here, you get 28 by 15, you get the beta value to be this. Oh, by the way, you can go and check the lambda value for all of them. Sorry. You see, we just found this beta. You can always go and find the beta naught using this equation. Using this y bar equals to beta naught minus x bar, this beta. So if you want beta naught is actually going to be y bar minus x bar beta, or beta x bar. So once you have this value, which is your beta, you substitute that here. As for these two, they are the means of x and y. You substitute that, that will always give you this. We are not interested in that. We are interested in the coefficient. That's it. And that gives you the value of this under range. Now, under elastic net is combining these. So elastic net, we decide to use a lambda value of 0.1 for the lasso, and then for the second one, which is the range, we just split it 50-50. So you just have to substitute that 50-50. Okay? And that will still fit with this equation here. Remember, we still have our 28 minus this. It's just that 0.5 is all we are doing. We are doing that 0.5 and splitting it into 2, because remember, it is a lambda 1 divided by 2, all divided by lambda 2. Okay, and lambda 1 divided by 2 will give you 0.25. The lambda 2 itself is 0.5. You substitute this, and that will give you 1914. Now, I want you to check something. So this is elastic net. Watch the elastic net value. This is a range. Range is 1.867. Okay, this is 1.96. So remember, lasso is higher, range is lower, and elastic net is always between the two of them. So elastic net is actually between the two, but then the OLS is higher than all of them. So you can compare this and see which model is the best. Okay, that is for later matter to know which model is the best. Okay, we are done. Now, can you solve this in Python? Yes, but I'll solve it in R because R does better work. So, and the reason why I say I'll solve it in R is because Python introduces two things, which changes the results. There's a lot of scaling that is done there. You see, we don't want scaling. But when you have your real data, you have to do scaling and normalization. Okay? But Python does that scaling here on this small data that we don't want to even change. So that's why I decided not to use that. But let's see whether we can use R to quickly run the results. I have all the codes there for you. Okay, so this is a data set. I want you to look at the data, 1, 2, 3, and then Y is 2, 4, 6. Okay, let's run the X variable. Look down here. So we have the X nicely showing. Okay, so we run the X, let's run the Y, we run the Y, okay, and you can always see the X and see the Y. Now we have to do sum of the x, y. You remember, sum of the x, y. That gave us 28. Let's run that and see. This is the sum of x, y. Let's see the result. Look down there, you have 28. Let's do the sum of x2. And let's see the result of that. Highlight and run that. That is 14. We had that. Now let's run the normal regression. I'm just going to run this normal regression for the beta. Okay, for the beta, and then I show the result for the beta. So we had the beta coefficient to be what? 2. And you can see that the normal regression is showing us a value of 2. Let's run for the range regression. The range regression, we set the lambda to 1. In fact, let me run the lasso first, because we did the lasso first. Okay. So this is a lasso, lambda is set to 1. Okay. We take the z value and we take the sum of it, and then we find the beta, putting them all of them into the formula. Let's see the value. 1.964. I'm sure you remember that that was exactly the same thing we had. 1.964 for the beta coefficient. What about the lambda? The range. Range 2, we set this one to 1, and then we found, I'm just putting them into the formula. We had 1.866. If you can remember, we had the same 1.867. And then we realized that the elastic net should fall in between these two. Do you remember the value of the elastic net we found? Who can tell me? It was 1 what? Who can guess? Ernest?
1.91.
So let's run the elastic net and see. So that one, the first one, the lambda was set to 0.5. The second one, the lambda was set to 0.2. Then the two values, the beta elastic net was done using this formula. Let's run this and see the formula. 1.91, So you can see that now we have been able to estimate each one of these values very, very nicely. Okay. And we've been able to set it up. And it is so cool. There is another way you can run this using another software. We can do that later, but at least this is to give you the idea that why are the values smaller than OLS? Because OLS had a couple of issues related to multicollinearity or related to heteroscedasticity or autocorrelation and things like that. There are certain issues related to OLS, and that brings the coefficient down. That's all. It brings the coefficient down. The significance of the coefficient, no wahala, but this brings the coefficient down. Ladies and gentlemen, that brings us to the end of the entire caboodle.